talk about extension of the merge sort that we just saw, we just see, called three-way merge sort. Okay, so well, so now this algorithm is very similar to, just now in the divide and conquer algorithm, we said that we given the input array we want to sort, we first cut it by half into two portions and then sort each one separately. Okay, and then we merge them. Okay, and you may ask, why by half? Why don't we say cut it into three pieces? Okay, so you're given the input array. So first I cut it into three pieces. And then I sort each of them individually. So after sorting, let's say they change color. They become sorted. And then I merge this 3-1 into a single sorted array. So why can't we do this? Okay, I call this a three-way merge sort. Okay, and the pseudocode is given here. What you see here, M1, M2, those are simply the breaker to break at 1/3 and then 2/3. Okay, that's all. Okay, all right. The question is that does this one also give us similar time complexity? Okay, in fact, if you look at what is the time complexity of this, okay, again we use T of n to represent the worst case time complexity of the algorithm when you sort it on a subarray of size m. We see that, okay, the merging part can actually be done in the same asymptotic time by performing the previous merge algorithm twice. So first we merge A1 and A2. Then we merge the resulting of the merged A1, A2 with A3. Okay, so that takes a linear time. And this is the same algorithm, but now on a subarray of size n/3. This is also n/3. And this is also n/3. So the time complexity of our algorithm becomes 3m plus. So these are the three recursive calls. This is the time for merge. Okay, so this is the recurrence that we have. Okay, now how to solve this recurrence? Well, it turned out that if you do the unrolling, then you see something very similar to before. So what happens is that when you unroll it once, every time you use this recurrence to apply to another subproblem, inside you will divide the size by another factor of 3. While outside, you have to multiply by another size, factor of 3. So when you write it out, you see this is 3 squared. Okay, and this term give you another Cn here. Okay, and if you do it one more time, you realize that, okay, then inside the problem size has to divide by another factor of 3 because of this. So that's 3 cubed. And outside, you have to multiply by another factor of 3. So you already have 3 squared, multiply by another factor, you get 3 cubed. And outside, this will give you another additive factor term of Cn. So now you have 3 Cn, and so on. And in general, you have now the stopping criteria is the same, which means that 3k equal to m, which means that k equal to log m base 3, and this then becomes n times t of 1 plus cn times log m base 3. And this is still dominating of the same order of n log n. So asymptotically, we get the same time complexity as before, which is n log n. Okay, In other words, in short, using a three-way merge sort asymptotically give us the same time complexity of the two-way merge sort. Okay, so it doesn't, cutting it into more smaller pieces is not really helping. Okay, all right, I want to say a few more words about it, that intuitively, why is the merge sort two-way or three-way? It doesn't matter. Why is this divide and conquer help? Okay, why by cutting this, we are saving time. Intuitively, by cutting them into smaller pieces intuitively, okay, we kind of reduce. So before, if you want to solve the entire thing, you may have to compare a number here with some any pair of number, one from here, one from here, okay? But now by solving each of them recursively, you first solve each of a subarray. Once they are sorted the subarray, remember that during the merge, this merge now, I don't have to compare each one with everybody here. The merge, because this is already sorted, remember the way the merge algorithm works. Every time I just need to compare one number here with some number here, which is the current smallest from the other side. Okay, so in other words, by sorting them first, now they are structured for this two subarray. And now when I merge them, I kind of save on, I no longer have to compare every, so before you have an n over, oops, you have an n over 2 points here. And n over 2 here. Then compare every pairs here that give you n over 2 times n over 2 minus 1 possible pairs. Okay, that you have actually n over 2 times n over 2. You have to potentially, worst the case, compare n over 2 times n over 2 comparisons. But now, once this individually, each subarray is already sorted, merging them, you only need, as we saw, the merge procedure, leveraging the sorted substructure, only takes linear now. This can be done by linear instead of n over n squared. That's where we are kind of saving, okay? Of course, the cost that we have the extra log n factor, because that this divide and conquer itself has to iterate, you have to do this for log n layers. So that's where just now when we compute the k equal to log n, okay, that's where this extra log n factor comes in. So the merge has to be done log n times, basically. Okay, so in the end, the time complexity and log n. But this is the intuition why this divide and conquer helps. Okay. All right. Okay, so I think that's all that for the time we have. Hold on.